In this lesson, we're going to look at how to calculate kinetic, potential, and mechanical energy. Now, the lesson went through what each one of these things are, so I'm not going to rehash that. I just want to do a couple example problems. So kinetic energy, remember, is the energy an object has because it's in motion. And it depends on two things. It depends on mass, and we're going to measure mass in kilograms, and it depends on velocity. Remember, velocity is speed with direction. We're going to measure that in meters per second. It turns out we're going to square that, which gets rid of the direction. So kinetic energy is not a vector quantity, it's just an amount. It's what's called a scalar quantity. And the equation for calculating kinetic energy is equal to 1/2 mass times velocity squared. Now remember your order of operations on that. The velocity gets squared first, and then you do the rest of the multiplication. So if we had a 3 kilogram object moving at 2 meters per second, we could get its kinetic energy. We'd say mass, 3 kilograms. Remember, this is how you start all your problems. You tell me what you know. It's velocity, 2 meters per second. We want kinetic energy. So KE is equal to 1/2 mv squared. We substitute in what we know. We know 1/2 of 3 times 2 squared. 2 squared is 4. Half of 4 is 2. Or 4 times 3 is 12, times half is 6. So we have 6 joules. Remember, the unit of energy is joules. In this case, we found that by taking kilograms times meters per second times meters per second, because we had velocity squared, which is a kilogram meter squared per second squared, which is the same thing as a newton times a meter. Anyways, kinetic energy, pretty straightforward, 1/2 mass times velocity squared. In the event that you have to solve something for velocity on that, remember how you would do that. So if I have KE is equal to 1/2 mass times velocity squared, I can multiply both sides of this equation by 2 to get rid of my half. So now I have KE times 2 equals mv squared. And then I could divide both sides by m to get rid of that m. So now I have KE over m times 2 equals v squared, and remember, to get rid of the square I have to square root. So you might see that the velocity is equal to the square root of twice the kinetic energy over mass. That equation is valid if you're solving for velocity as opposed to kinetic energy. Now another one we want to look at is potential energy. Now this one often gets messed up because students think that potential energy must be the opposite of kinetic energy. So if kinetic energy is the energy something has because it's in motion, potential energy must be the energy something has because it's at rest. That is entirely false. Potential energy has absolutely nothing to do with something's state of motion. It could be moving, it could be at rest. It doesn't matter. That doesn't affect its potential energy. Its potential energy depends only on forces that are trying to get it to shift. So there's potential energy between atoms because their electrons are attracted to protons and they want to bond. There's potential energy of a rock that can move down a hill because gravity wants to pull it. But that potential energy is still there halfway down because gravity is still attracting it towards the ground. There's potential energy in a spring because it's stretched or compressed. It doesn't matter if it's in motion or not. It's got potential energy if there's a force acting on it trying to make it change. If it's got a potential to change, it's got potential energy. We're only going to concern ourselves in this with gravitational potential energy. So this is GPE, or sometimes I just say PE. This is the energy that something has because gravity is pulling on it, and it is equal to mgh. Remember, g is the acceleration due to gravity on Earth. That's 9.8 meters per second. M is, of course, mass in kilograms, and height is how high this thing is above whatever zero we pick. We usually pick 0 to be ground level. So if we have a rock on the top of a cliff and it's got a mass of 4 kilograms and it's 2 meters up, then we could say its potential energy is given by mgh, and we have m is 4, we have h is 2, this is meters, kilograms, this is meters, and then we have g here on Earth, 9.8. So we're going to take 4 times 9.8 times 2. Let's see, I believe that's 78.4, and this is also joules. Here we arrived at it a little bit different. We took mass, kilograms, times acceleration, meters per second, times distance in meters, but you'll see that's still a kilogram, meter squared, per second squared, which is in fact a joule. So potential energy, mgh, that one's fairly straightforward. And then, of course, we have what's called mechanical energy. Now, mechanical energy is the energy an object has, and it's just the sum of its kinetic and potential energy. So, lazy here, abbreviate that. Mechanical energy is kinetic energy plus potential energy. It doesn't matter, again, this could be in motion, it could be at rest, it could be up on a hill, it could be halfway down a hill, but in any of those locations it'll have some value of kinetic and potential energy. Sometimes they're both zero, sometimes they're not. And so if you have, say, something that's coming down a hill, let's say it's right here and it's 4 meters up, it's got a mass of 1 meter or 1 kilogram, and it's moving with a velocity of 3 meters per second, and I want to know its mechanical energy, you would say, all right, well, mechanical energy is equal to Ke plus Pe, which in this case is half mv squared plus mgh, and so then we can plug in what we know. We know 1/2 mass is 1, velocity is 3, remember square that, plus m is 1, g is 9.8, and it said h is 4. So 9 times 1/2 is 4.5 plus 39.2, and so we get 43.7 joules, right? So we just do the two of them together and then add them up for mechanical energy.